Hey guys, it's Dr. J, fresh back from winning state. We won state. So today we're going to do some more experiments, okay? And we're gonna study energy in the real world around us, okay? And as usual, we're gonna make use of our trusty golf balls. So how are we going to do this? All right, and how are we going to study energy? So one of the things we'll be turning in today is an updated introduction section, right? So we've got 2 new questions right here. So when a ball bounces on the ground, does the ball retain? That means keep all of its kinetic energy? Well, we'll find out. And in this lab, how will we study energy efficiency? Okay, so let's start talking about those 2 questions. So here I've got a golf ball, right? And we've all dropped golf balls plenty of times by now, right? So let's go ahead and drop this one. So I'm gonna drop the golf ball, right? And right here, it's got a certain amount of gravitational potential energy, okay? And that potential energy is gonna get turned into kinetic energy. It's gonna get turned into kinetic energy as the ball falls toward the ground, right? Or toward the table in this case. Here we go. So it gets dropped. But notice, each time the ball bounces, it stops and then begins falling again a little bit below its previous height. Like the ball's never going to get to my hand again. I'm going to drop it from here. It will never return to my hand. Right? Never return to my hand. Okay? And it gets a little bit lower each time. So what that means is that this ball doesn't keep its kinetic energy, okay, as it bounces. Every time it bounces, it loses a little bit of kinetic energy, okay? So we're going to study energy efficiency in this lab by dropping a golf ball from the balcony and then calculating the efficiency with which the ball bounces, okay, the energy efficiency. So that's how we're going to study, all right? So if we go back to the questions, right? When a ball bounces on the ground, does the ball retain or keep all of its kinetic energy? Well, no, because it doesn't bounce all the way back up, okay? After it hits, it loses some height and therefore it loses some kinetic energy or some potential energy, depending on how you want to look at it, with each bounce. And in this lab, how will we study energy efficiency? Well, we're going to drop a golf ball from the balcony and we're going to calculate the efficiency with which the ball bounces on the concrete, okay? So that's how we get through those 2 questions. So I would say update your introduction right now because you're going to turn that in today with your assignment, all right? And so now let's talk about how we're going to perform our calculations or how we're going to collect our data. All right, so we're going to go out to let's look at our steps here first. So we have our golf ball, our timer, and a gram balance. And we're going to use the gram balance to determine the mass of the golf ball. And we're going to drop the golf ball, as in previous labs, from the balcony and time the ball's descent to the ground. And we'll do that like we always do, 3 times, okay? So that's just the trial that we've always done. And those data will go right here, trials 1, 2, and 3. And then this will be our average, right? So I'll go ahead and program that in right now. So that equals average, right, of C3 to E3, right? Boom, just like that. And then I'll go ahead and just set this up. So these are all taken care of for you, okay? So all you have to do in this case, and this is easy, I know you can do it yourself, but I just knocked it out for you. You have to put your data there, okay? And then you'll get an average here. Now, next up, we're going to do another drop trial. So the way this trial is going to work is you're going to drop the golf ball from the balcony, and I'll go ahead and blow this text up so we can see it a little easier. We're going to drop the golf ball from the balcony and record the amount of time until the golf ball makes its second bounce or impact with the ground, okay? So, and you're going to record, and so you're going to perform that trial 3 times. So how does that one work? So the second time you drop the ball, it bounces once, and then when it hits the second time, that's when you stop your timer. So you start your timer up here, right when the ball gets dropped, then you're going to let it bounce, and the second time it hits the ground, you're going to stop your timer, okay? And those data are going to go right there, all right? Finally, we're gonna time how long it takes for the golf ball to make its third impact with the ground, okay? So this trial, we drop once, bounces, then we let it hit a second time, and then when it hits the third time, we finally stop our timer, okay? So this time it makes 1, 2, and we stop on the third impact with the ground, all right? And so that's gonna give us this final average here, all right? And so I'm gonna go ahead and plug in just some dummy numbers so you can get a rough idea of what to expect. These are numbers that I've actually these are data that I've collected myself, but they're very rough. So your numbers should be not too far maybe from my numbers, but they shouldn't be the same as my numbers. Your numbers should be better than mine, okay? So the first drop always takes 1 second, okay? And then the second drop time has to get calculated very carefully. So let's say that on trial 3 here, I got 1.0. And then on trial 2, I got roughly 2.7. Well, what's interesting is we would have to divide what we'd have to do in this sort of situation is we'd have to do 2.7 seconds minus 1.0 seconds. That's going to give us 1.7 seconds, right? But those 1.7 seconds are the time that it takes the ball to go from the ground all the way to some top point and then back down again. But all we really care about is the time that it takes for the golf ball to drop from here to here, okay? That's how we've done all of our measurements. Our initial measurement is just the amount of time it takes the golf ball to drop straight down from the balcony. So what we care about isn't this entire 1.7 seconds, which is what's required to go, again, this entire arc, but it's actually all we really care about is the amount of time that it takes for the golf ball just to drop straight down once. So we have to divide that by 2, okay? So what I'm gonna do is I'm gonna program that calculation here for you, okay? So let me clear all of that. So the way that I'm going to do this is just to click here. So this equals, okay? This equals, so this one is just equal to, no, sorry, let me fix this. So this one just equals F3, that's easy, F3, okay? This one equals F4, and I'll use parentheses, F4 minus F3 all divided by 2, okay? That's what that's equal to. And if finally over here, what I got was roughly 4.2, and that's about what I got, right? Then if I drag this guy down, will it get it right? Yeah, it'll get it right for me. Okay, you can drag down. That one ends up being F5 minus F4. So this one minus this one, okay? All divided by 2. And each time what I'm looking at, what I'm trying to get, so we have our first drop, and then it bounces, and then it bounces again. And so our first drop time gives us the amount of time, and let me circle this in blue so you can see. Our first drop time gives us the amount of time, okay, here. Our second drop time gives us this amount of time from the peak of the first bounce, okay, to the beginning of the second bounce. And then our third drop time gives us the amount of time from the peak of the second bounce, okay, to the beginning of the third bounce, all right? And we need those specific times in order to calculate our height, which we're going to need in order to calculate energy, all right? And so I'll go ahead and show you how those calculations are performed, all right? So the distance, okay, which is equal to the height, the distance that a golf ball falls is equal to 1/2 times the acceleration of the golf ball times the amount of time for the fall, okay? And that's the fall from the top, all right? So in any of these cases, right, distance equals 1/2 times 9.8, which is gravitational acceleration, times, oh, and this needs to be squared, times the time squared, okay? So for my values, and I'll go ahead and put this in for you. This is 0.5, which is 1/2, times 9.8, which is gravitational acceleration, times, and my time was g3 squared. Okay, and this autofill works just fine. All right, so that gives me my maximum height. Our mass in kilograms is something that you're going to have to plug in, but I'll go ahead and plug in 0.046 kilograms as a placeholder. Okay, and then I'm just going to move that on down. And because I'm thresholding at 2 decimals, it's going to show up as 0.5, but the program knows that it's 0.06. And if I want to, for that cell, I can give one more decimal. Okay, and this is the one that you need to do, the maximum potential energy. So follow closely because I'm not gonna plug this in for you. So you need to remember that potential energy, which is this guy right here, equals mass times gravity times height. Okay, so what you have to do is you have to plug in, okay, your height value. So this, in this case, for this particular cell here, that's going to be H3. Okay, this guy is H3. So height times mass, which is I3, okay, times gravity, right, which is 9.8 meters per second squared. Although in Excel, you're not going to use the unit, just use the 9.8, okay? So you're going to multiply all of those together to get what's in this cell, all right? So these guys you are responsible for, okay? You're responsible for these guys, all right? So like if I were going to type this in this case, it would be equal to mass, which is I3, times gravity, which is 9.8, times height, which is H3, right? And that's the energy value that I would get. And yes, the autofill would work, okay? But I'm going to delete all of that so that you'll have to do it on your own. Now the efficiency, okay, the efficiency is the energy value here divided by the energy value here. And this last one's going to be NA, okay, not applicable because we're not going to actually measure the efficiency of the third bounce because we don't time how long it takes to get to the fourth bounce, all right? So here we go, equals J4 divided by J3, all times 100. Okay, and then this one equals J5 divided by J4, all times 100. All right, so just like that. Okay, and that's how we're going to get our efficiency values, and that's been plugged in for you. So the only values you have to plug in, okay, the only formula that you're going to have to plug in is that one right there. And I'm going to go ahead and erase these values, and I'm going to erase these values, okay, and you are going to be on your own. All right, but as always, you won't be fully on your own. You're going to be working with your group. Okay, so again, as always, good luck, and may all the forces be with you. All right. Oh, last bit of business. What you're going to turn in are 2 things. Okay, you're going to turn in this spreadsheet and your updated copy of the introduction. Okay, and you can turn in the materials and methods with it. Obviously, these get left alone. Okay, the only 2 additional questions you're going to need to answer are these, but do go ahead and include your answers to the first 3 guiding questions. All right. Okay, so once again, good luck, and may all the forces be with you.